Hi guys, welcome to this class where I'm going to make real numbers really easy for you. This is also called number system in some of the textbooks. So whether you call it real numbers, number systems, let's get these number concepts crystal clear. Keep your pen and paper ready and let's begin. Before we get started, I just want to say do check out the other courses on our website. If you haven't done so already, we have physics, chemistry, biology, and maths for CBSE, ICSE. We also have the Cambridge IGCSE International Board. And guys, check out our AI, our new course on artificial intelligence. We have Java and Python coding for all classes. So do share it with your friends and make sure you have also subscribed to our YouTube channel. With that, let's begin. We are using numbers all the time in our daily lives, right? Like let's say our mother tells us get some, a dozen apples, or in this picture, I think there's 16 apples here. So you can see in this box, that's the number 16. Oh, I'm feeling hungry seeing this pizza. If I eat this pizza slice, how much of the pizza I've eaten? Can you see there's 1, 2, 3, 4, 5, let's say 6 pieces here. If you eat one slice, you can't say you've eaten one pizza, you have eaten 1/6 of the pizza, right? Fractions. So we are using these natural numbers or whole numbers. We are using fractions. If you eat, let's say, this part of the chocolate, how much of the chocolate you have eaten? 3 divided by 8 pieces. So again, a fraction here. Let's say you've got some money in this piggy bank. Let's say you have 21.50 rupees. So that's a decimal number. We use decimal numbers. Can you guys recognize this number? Let me read it out for you. 3.1415926538535897932. Anybody recognizes? Wow, you guys are fantastic. Chatura, Ashmit, Sayan, Jishnu, Jairam Kaushik. Everybody has the right answer. Tamogna, very good. So this is nothing but the value of pi. You'll say, why is it so long? Yes, it's crazy. And we're going to go talk about pi today. The famous pi of mathematics. So there are lots of numbers, and there's this important term. All these numbers are called real numbers. So question is, how do you define? So all the numbers we talked about, right, in this previous slide, these are all real numbers. Now, how do we define what are real numbers? Can you guys tell me? What are real numbers? Every number is a real number. Integers, rational, irrational. See, I'm getting different answers. Numbers starting from 1, those can be shown on a number line. Okay, many this thing here. So I'll come to that question. First, let's talk about the simple numbers that we know already. You guys have heard of natural numbers? Can you give me an example? What are natural numbers? Natural numbers are when you start from 1, like 1, 2, 3, 4, 5. These are natural numbers, right? Counting numbers starting from 1. Next, you guys know what are whole numbers? Natural numbers we represent with the symbol n. Then you have whole numbers. Whole numbers we represent with w. What are whole numbers? Again, natural numbers. The only thing is you add a 0 to that. So 0, 1, 2, 3, 4, 5, and so on. Then what else you know? There's something called integers, which is represented by z or I. What are integers? They are all the whole numbers and then negative numbers as well, like -3, -2, -1, 0, 1, 2, 3, and so on. So all whole numbers and their negative are integers. Can you represent all these on the number line? You guys have heard of this number line, right? So you have 0 in the middle, you have 1, 2, 3, 4, 5. So all these are numbers on the number line. Like natural numbers we can put over here. 1, 2, 3, 4, 5, and so on. Whole numbers is all these natural numbers and the 0 as well. Integers are all these numbers and -1, -2, -3, -4, -5, and so on. But now the question is, are there more numbers on the number line beside these ones? Yes, certainly. Why not? There is the number, you have half on the number line, which is exactly between 0 and 1. Then you can have let's say we can have a 2.7 here, right? We can have a -2.5. We can have a -half. So what are all these numbers? What do you call these that I'm putting over here? Fractions, decimals, very good. These are in fact called the rational numbers, right? So all I'm showing over here, these are all rational numbers. which are all these fractions and decimals that we'll talk about in P by Q form. They can all be put on the number line. And then are there more numbers on the number line besides decimal and fractions? Yes, there are something like, you can have the value of pi, you can have root 2, root 3. There are so many more numbers on the number line. So the collection of all these, this natural, whole number, integer, rational, irrational numbers, all of these together are known as real numbers. And real numbers you can visualize, you can plot them on the number line. So real numbers can be plotted on a number line. Clear? That is the meaning of real numbers. Now question is 0 a positive integer, negative integer, or is it neither positive nor negative? So 0 is right here in the middle. Here you can see all the positive numbers, here are all the negative numbers. So here we can say the answer is going to be, it is neither positive nor negative because it's in between. Is 0 an odd, even integer, or is it neither odd nor even? Do you guys know the answer for this? I think Sayan has the right answer. Anybody else? 0 is considered even. Why? Because even means something which is divisible by 2. 0 by 2 is 0. So it's divisible by 2. Answer is an even integer. This chart is very, very important. I want you to visualize this, right? In fact, you can even draw this and we're going to discuss because there's so many terms over here, you can see, right? And we are going to understand how real numbers are divided like this. Till now, we have done the easy stuff, right? We have talked about the negative, we have talked about the natural numbers like 1, 2, 3, 4, and so on. These are also called counting numbers. If you add 0 to that, then together they are known as whole numbers. And then negative integers, you guys know, minus 3, minus 2, minus 1, and so on. So you guys are familiar with all of these? And together, these are all known as integers. But what are rational, irrational, all these non-integers, terminating, recurring? Let's talk about. And remember, these all come under real numbers. So first, let's talk about what are rational numbers. The easiest way to remember this is rational numbers can be expressed in P by Q form. P by Q, P and Q are variable like X by Y, 3 by 5, 2 by 3, right? So basically you can remember rational numbers are fractions because you can express it as a P by Q form. So easy way to remember, hey, these are fractions, P by Q form, where P and Q are integers. In some books you'll also written it's co-prime, which means they don't have any common factor. Like if they had a common factor, you have cancelled it. For example, if something was 6 by 9, you will not keep it 6 by 9. You will cancel and simplify it to 2 by 3. Correct? You will divide both numerator denominator by 3. So many times you'll see it's written as they are integers. They are called co-primes. No common factor. Now, why this restriction that Q is not equal to 0? Why do we have this restriction on rational numbers? Imaginary numbers, very good. So that is out of the syllabus, right? Right now that you can have numbers which are imaginary or not real. Okay. So, but why this restriction that, hey, P by Q is integers, but Q should not be 0. So you take an example. If I tell you guys, hey, let's do 3 by 0. What is the answer? What is 3 divided by 0? You have 3 chocolates and 0 people to eat it. How much does each one get? In mathematics, this is considered undefined. This has no meaning. 3 by 0, undefined. It's like a crime in mathematics. So that is why we say, hey, Q better not be 0. Okay, Q should not be equal to 0. So we say rational numbers are P by Q form. Is 7 by 4 a rational number? Yeah, it's like error in computer. Error. Exactly. So 7 by 4, see, it fits P by Q. And if you do 7 by 4, what is the value you guys are going to get? If you do this division, 7 divided by 4 is, I think, 1.75. So yes, rational numbers can also be, P by Q can be converted to decimal form as well, as you can see here. What about 1 by 8, guys? That is also rational, P by Q form. Can you convert it for me? What will you get if you do the division? 1 divided by 8, come on, do it, guys. I think 0.125. See, again, it gives you a decimal number. No problem. What is 4 by 3? If you guys do the division, don't use a calculator. Try to do it yourself, right? Without any calculators. What is it? Very good. 1.33. But how many 3 should I put here? 1.3, 3, 3, 3, 3, 3. It just goes on and on. What do you call these kind of decimal numbers which don't stop? They are not, when you stop, we call it terminating decimal, stops. This guy is not stopping, irritating guy. It is non-terminating, or we also call it, since this 3-1 is repeating, it is non-terminating and recurring. So you must have seen this notation in maths. We write it as 1.3 bar or 1.3 dot, because this 3 bar means 3 is repeating again and again, 3 dot. Okay, these are the irritating numbers, not terminating. So what we can say, rational numbers can be terminating decimal, which means they finish off, not going on and on, thankfully, or they could be non-terminating, which means it's never finishing, but repeating. Can you see the repeating pattern? 3 is repeating. So they can also be non-terminating, not ending, and recurring. Recurring means repeating. Exactly. Yes, Rishabh Banerjee. It's going on and on. 1.3333333. Okay. So this is one thing. A lot of students have confusion. So first of all, in summary, what have we done? Rational numbers are P by Q form, fractions. If you sit and divide them, it may terminate, which very nice. It has stopped. Or there are two options here. It may either terminate, terminating decimal, if you do the division, or it can be not ending, non-terminating, but repeating pattern, recurring. Those are the only two possibilities. Nothing else is possible. Clear? So please write that in your book right now. Rational numbers means terminating decimal or non-terminating, never ending, but repeating, and recurring or and repeating. Have you guys written that? Please write it down. Now the question is 3 a rational number? What do you guys think? Yes or no? So I can see most of you are telling me yes, and you are absolutely right. 3 is of course a natural number. It's a whole number. We can consider it integer. But why is it a rational number also? Because 3 I can write it as 3 by 1. And there you go. I have proved it to you. It's P by Q. So the answer is yes. What about 2.5? Is it a rational number? Again, same trick. See, decimal you can always convert to fraction. So 2.5 is 25 by 10. Now it doesn't look nice. Maths teacher will not like if you have not simplified it. So you should write no, 5 by 2 will cancel by 5. And that is also P by Q. So the answer is going to be yes, yes, yes. So if I can express it as a P by Q form, a fraction form, we are good. Now if I ask you this question that, hey, I've given you some fractions, right? These are all rational numbers. They're all P by Q. Now I'm asking you, because I told you rational number can be either terminating or non-terminating and recurring. So can you guys tell me, is this going to give me a terminating decimal, or by recurring, I mean non-terminating, right? Repeating pattern means it is not ending. So sometimes you will see that non-terminating word is not written there. It's directly written recurring. So can you tell me which of these are terminating or recurring? One very simple technique is sit and do the division. So if you sit and do the division 1 by 7, what will you guys get? So please sit and do the division. I'm going to be a little lazy here and use the calculator, but you guys don't do that, please. Very bad thing that I'm showing here. But just to save time, I'm going to use the calculator. Okay. So if I use the calculator and I do 1 divided by 7, I'm getting 0.142857142857 and so on. So what is this? It is not ending. But can you see that there is a repeating pattern here? Can you guys see? 142857, 142857. So this I can write it as 0.142857 with the bar on top, or some books write it like this, 0.142857. Since this whole part is repeating, we put a dot on top of 1 and a dot on top of 7. Is it clear? So that is one way you can easily check. Similarly, if you do 19 by 50, this one is easy to divide. In fact, I can show you a nice trick. If you have 50, you just multiply the numerator by 2 and the denominator by 2, because I'll change it to 100. So what is 19 times 2? 19 times 2 is 38 divided by 100, 0.38, right? That's it. So what did we get here? Here we got a recurring decimal. Terminating, non-terminating, not repeating and recurring. Here we got a terminating decimal. What about the last one? 43 by 150. So please check it. Again, I'm going to be a bit lazy here and do the division. 43 by 150 with the calculator. And don't do this. I'm just doing it to save time. 0.28666666. It's just going on and on. So it is clearly recurring, not terminating. And you can see I will write it as 0.28. Only the 6 is repeating. So we'll put a 6 bar, or we can say 0.286 dot. Please don't put the bar or dot above 28 because that part is not repeating. The first one also, if you keep dividing, you'll keep seeing this 142857, 142857. You keep doing it, it's keeping on repeating. So this entire pattern is repeating. Here only the 6 part is repeating, so we write it like this. So this is also a non-terminating recurring, or we can simply write recurring, repeating pattern. Do all of you agree with these answers? But this is time consuming, right? We are having to do division. Is there some magic trick where I can give the answer of terminating or recurring even without division? Is there some magic trick? The answer is yes. It is a very simple trick. What is the trick? You just have to look at the denominator of the fraction, not the numerator. Don't even look at the numerator. Look at the denominator of the fraction and check if it has factors of 2 and 5 only, then it will terminate. Otherwise, all other fractions give recurring decimal answers. So what is the shortcut trick? So you can say shortcut is if denominator has factors of 2 and 5 only, then it is terminating. Otherwise, it is otherwise not terminating. Otherwise, it is recurring, because in rational numbers, you always get a non-terminating repeating pattern. Is this clear to all of you? So that is the quick trick. That's the check you have to do. So you guys can go and check that. So let's apply that trick here. 7 is the denominator. Is it having factors of 2 and 5 only? No, there's only one factor here, 7. It will be recurring. See, this is what we got. 50. What are the factors of 50? If you break down the factors of 50, you can see 50 has the factors 2 times 5 times 5. Factors of 2 and 5 only, terminating. 150. What are the factors of 150? We have 2 times 3 times 5 times 5. Check it. 25 times 2, 50. 50 times 3 is 150. But the problem is factors of 2 and 5 only. There are 2 and 5 factors, but 3 is also there. This Mr. 3 has spoiled it, right? And that is why it is giving a recurring decimal number. So this is the simple magic trick. All you have to do is just check the denominator. You don't even have to do all that division. No need of calculator. Just check if the denominator has factors of 2 and 5 only, terminating. If it has more, if it has other factors, it is recurring. Crystal clear? Is this magic trick clear to you? And yes, that is why in many of the books, this trick is written like that 2 and 5 only, they write in the book as 2 to the power m, very good, and 5 to the power n. Basically saying that, hey, the denominator should be only 2 to the power. So it doesn't have to have 2 and 5. It could be only 2s, like half, 1/4. These are terminating. 1 by 5, 1 by 25, also terminating. So it doesn't mean it has to have 2 and 5, but 2 and 5 only, nothing more than that. Okay, Ankit Shah, is that correct? So Ashmit is asking, is non-terminating and recurring the same? No, it is not. We are coming to that. There are some decimals which are non-terminating, but they don't repeat. Okay, there can be decimal numbers which are non-terminating, like pi. They never finish, but there is no repeating pattern. We still haven't found any repeating pattern. Okay. But when we say the word recurring, repeating, it has to be a non-terminating. You cannot say, hey, this is a recurring decimal, because it stops. There's no repeating pattern. Okay, exactly. They are irrational numbers. Ankit Shah, correct. We are coming to that. So Nehashree, as I said, if the denominator has factors, so you find the factors of the denominator. If it has factors of 2 and 5 only, then it will terminate. It could have factors of only 2 or only 5 or both. 2 and 5 basically means only 2, only 5 or both. But if it has some other factors like 3, 7, prime factors, of course, or 17, 11, then it will give you a recurring. And you guys can check that. So this is another related question. What type of prime factors the denominator of each of the following has? So this is the reverse question. We have given you the decimal numbers here. You have to tell the prime factors of the denominator. So we can use that trick because we had learned that if it is terminating, like this guy is terminating, right? So if you look at this fellow, this is clearly a terminating decimal. Now, because it is terminating, so we can say the denominator is of the form 2 to the power m, 5 to the power n. What does this mean? Only multiples of 2 and 5. So we can say prime factors of the denominator are 2 and 5 only. That's it. Clear? Now, what about this one? 6.1324. But you can see there is a bar here. That means this is clearly recurring, repeating. So therefore, denominator has factors other than, or prime factors other than 2 and 5. Here, it has to have some more factors. What about this one? 0.21, 221, 2221. What about the last one? The problem here is that there is no repeating pattern because 21, then you have 221, then you have 2221. So there is no repeating pattern. So what is the problem here? This guy, we say it is not recurring. It is non-terminating. As you can see, it is never ending, but it is not recurring. So therefore, it is not a rational number. If it is not a rational number, is there any question of a denominator? Is there any question of P by Q? If it is not a rational number, what do you guys think? So because it is non-terminating, not recurring, so there is no question of a, question of denominator does not arise here. So this is like a trick question. It's like none of these, right? Next, let's talk about irrational numbers. So we have all been talking about rational numbers. Let's get a bit irrational right now. What are irrational numbers? Those numbers that cannot be expressed in a fraction form. You can't express it as a P by Q. No, there is no magic fraction that will express. What are some examples? Square root of 2, root 3, cube root of 10, pi. And the examples we discussed, right? If you have decimal numbers which are non-recurring, that means they are clearly irrational. Okay. And you guys can check this. If you look at the value of square root of 2, what is the value? Obviously, this I can't calculate a very accurate value, so I'll have to use the calculator here. So square root of 2. Square root of 2, if you look it up in the calculator, if you want to see many decimals, is 1.4. You might remember 1.414, but it doesn't end there. 1.4142, 1356, 237, 3095. It's like one long phone number or something, right? But the problem is there is no repeating pattern. It is non-recurring. Same thing if you look at root 3. You guys check. Can you find any repeating pattern here? You'll get a Nobel Prize for sure in mathematics. We know root 3 is 1.732, but that's only the approximate value. There is 05, 08, 07. Wow, so many zeros. 56, 8877. See, is there anything repeating here? And this is not just the end. You can go on and on, right? Same way for these things. And pi also 3.14159, right? It doesn't end. 3.14159, and it just goes on. Cube root of 2, what is it? 2.1544346900318884. I think you guys get the point. What is happening over here? These are all these numbers are non-terminating. The decimal number never finishes. It just goes on. Your division, your job never finishes. And it is non-recurring. There is no repeating pattern. That is why these are irrational numbers. Rational numbers are of two types. Again, I'm reminding you, please be clear. Rational numbers terminating, nice decimals, they finish off, or they are non-terminating but repeating. Opposite is irrational numbers. They are non-terminating and non-recurring. Is this crystal clear to you with these examples? So which of the following numbers are irrational? Can you guys tell me? So one nice thing about irrational numbers are all these square roots. These are called surds or radicals. These are usually irrational, right? So all these roots which are known as, these are all called surds or radicals. But this doesn't mean, does every surd and radical have to be irrational? Why don't you check? So is square root of 49 irrational? Don't look at the square root and say yes. Because we know square root of 49 is square root of 7 times 7. So the answer is 7 there. So that is definitely a rational number. So this is rational. What about cube root of 8? Again, don't see the cube root and get excited. You should simplify it. It's a cube root of 2 times 2 times 2. It's not that, hey, I saw the cube root irrational. No, no, no. Again, the answer is 2. This is simply a rational number. What about the last one, guys? Pi by 2. Can you guys tell me, is pi by 2 rational or irrational? So how do we know this answer? Pi is irrational. It is non-terminating. And if you divide that by 2, please don't take pi as 22 by 7. That's only the approximate value. Yeah, I forgot to mention that. Many of you might be thinking that, hey, pi is 22 by 7. So this confusion is there. Sometimes you think, oh, pi is 22 by 7. But no, guys, that is only the approximate value. Or sometimes you think, hey, pi is 3.14. That is only the approximate value of pi. The real value of pi, as we discussed in that first slide, is this big, huge, massive number which never ends. Scientists have not found, mathematicians have not found an end to pi. It means a repeating pattern. It can be non-terminating, but there's no repeating pattern also. Okay. So please, pi is not 22 by 7. So it's basically that massive number. If you divide by 2, so you have to think of pi like 3.14159, whatever, and it goes on and on. If you divide by 2, you are basically going to end up with an irrational number. Because dividing an irrational number by 2 is only going to give you an irrational number. 22 by 7, yes, that is the confusion. 22 by 7 is the approximate value of pi, not the real value. Okay, approximate. So in summary, again, I'm saying this chart is very important. Please draw it right now and fill in some examples with me. Okay, so please draw this chart quickly right now, because this will really get you the whole picture clear of what is all this real, rational, irrational, everything will be crystal clear to you. Pi is even or odd, Aditya. Even odd is only for integers, right? Pi is not integer, it's a fraction. So we don't say even odd. Okay, Aditya, Kishore. And pi is 22 by 7 is the approximate value, not the real value. So let's look at this chart, and it's always easy to start the chart from the bottom. Let's look with the examples. So whole numbers, natural numbers we'll start off with first. 1, 2, 3, the counting numbers. If you add 0 to that, it together becomes whole numbers. If you add negative integers to that, -3, -2, -1, together these are all known as integers. So integer doesn't mean only negative integer. It includes 0 and natural numbers. Okay. Now if you take integers, integers are rational. They can be expressed as p by q like we discussed. You can divide by 1. But then you have also non-integers, like there are fractions which terminate, like half, 0.5, like 1 by 4, or 1 by 10, 0.1. These are terminating decimals or non-integers. And then there is the recurring, which never ends, right? Like, for example, if you take 1 by 3, 0.3333, or we say 0.3 recurring. And remember, non-integers means they can be terminating decimal numbers or non-terminating but repeating. Recurring means repeating. These all come under rational. They can all be expressed as a p by q form. But those numbers which cannot be expressed as a p by q, they are called irrational numbers. For example, so these are not p by q, not in a fraction. For example, square root of 2 cube root of, pi, or the value of pi. These are all irrational and they are all non-terminating. The decimal never finishes. Non-terminating and non-recurring. There is no repeating pattern that the mathematicians have found here. So that is why it comes under irrational. Is this full chart clear to you? Very important. Can irrational numbers be represented on the number line? Wow, Nehashri, excellent question. And my next slide is, I think, on that itself. Because remember, we said all the real numbers can be represented on the number line. You can represent them on the number line. All of you know what is the number line. Rational numbers are easy, fractions and all decimals you guys can easily put, just divide it into parts and put it. But how do you represent irrational numbers on the number line, like root 2, right? How will you guys represent this? Let's take a look. So the next question is, how do I represent root 2 on the number line? Now, one option is you can say that, hey, root 2, I know the approximate value is 1.414. So I can, roughly put it. Will that be accurate? Will that be correct? The answer is no. That is not the accurate way to put it here. So how do you represent root 2 very accurately? Hint is using geometry. So how would you do that? So let's say this is the number line. So you have 0 here. So this is 0. This is 1. This is 2, 3, minus 1, minus 2, and so on. Any idea, guys, how to represent root 2 on the number line? So this will be an approximation. I can't do 1.414. So trick is, do you guys know Pythagoras theorem? Mr. Pythagoras, have you heard of Pythagoras theorem? Yes, yes. So why am I talking about Pythagoras theorem? Because look, we are looking for root 2. And Pythagoras theorem, if you guys remember, it is basically a right angle triangle where you have, let's say this is your, these two sides are A and B. Then what is the hypotenuse? It is square root of A square plus B square. Sum of square of the two sides and you take the root of that. And that is why we are going to use Pythagoras, because we want a root number. So if we can use a triangle and form that, somehow we can try to put it here using maybe a compass. So what should A and B be so that I get a root 2 over here? What should be the values of A and B? I want a square root of 2. And square root of 2 needs to be A square plus B square. So if you guys think carefully, if A is 1 and B is 1, square root of 1 square plus 1 square is exactly what I want. Square root of 1 plus 1. So we know the length of the hypotenuse is going to be root 2. You guys agree? Please look at this triangle. Very good. Yuvraj, Joy, Nehashri, 1, 1, right? Excellent. So that's exactly what we are going to do here. So if, see this 1 and 1, if I can draw this Pythagoras, using Pythagoras theorem, then this root 2 line is perfect in length geometry. It is accurately representing the length root 2. And that I just need to throw it on the number line. How do I do it? Very simple. You draw a triangle here. This is the length 1. And you want to draw perpendicular. All of you guys know how to draw a 90-degree angle using this compass, right? So you'll put all these arcs using your compass and draw a 90-degree angle, right? So all of you know how to draw 60, 120, bisect that and all of those business, or you can draw perpendicular. Yeah, so you'll need to do that here, right? So you basically draw a 90-degree here. Now, once you draw the 90-degree, you measure a length 1 using a compass. So take a compass and put the compass point here and mark the length of, so measure this length of 1 and use the compass to mark it over here, right? So we will mark a length of 1 over here using the compass. Let's say that is 1. And then when you join this line, when you join, that is basically your right angle triangle, and this has the root of length of root 2. But the only problem is that, hey, I just copied the triangle and drawn it here. I want the root 2 on the number line. How do you put it on the number line? Very easy. Again, use your compass tool. Put your compass point here. Accurately with the compass, put it over here. Measure this length root 2 using a compass. And then all you need to do is you need to drop this arc, this compass here. And there you see accurately you will get where it intersects the number line. is where you get your root 2. Did all of you get that? Put your compass point here, and with that length of root 2, with this length, you draw the arc, you will get root 2 very accurately on the number line. This is a very basic and important technique. I have some more details on more irrational numbers. You can watch my video, but root 2, and we'll look at another example. So we have talked about how to represent root 2 on the number line. We'll talk about how to represent root 3. Yes, there is semicircle method also. So Aditya, that's absolutely right. You guys can watch my video on the semicircle method. So there is a semicircle technique which is very useful for any general number, but that you guys can watch my video. Right now we are doing with the simple Pythagoras theorem. Now how do you represent root 3? Again, think of it. You need a triangle here. You need a triangle in such a form that its hypotenuse is square root of 3. So to get square root of 3, what do I need? So this is, remember, a and b. So this is square root of a square plus b square. Now let's say b is 1. What should my a be so that I get a root, so that I get a 3 within that square root? That means a square should be 2, right? Then 2 plus 1 will give me a 3. If a square should be 2, then a needs to be square root of 2. Please check that. Is this Pythagoras numbers correct? Square of root 2 is 2. 2 plus 1 is 3. See, root of 3. So I need such a triangle. Now, how do I get that? Very simple. Again, if this is your number line, okay, if this is your number line, first thing is you get root 2. How do you get root 2? We just did it. You get root 2 accurately using your compass and stuff, right? So first get root 2 on the number line. So you followed the previous steps and you got a root 2 over here. Now, since you have got root 2, you just need to draw your 1. How do you draw the 1? You draw perpendicular. How do you draw perpendicular? You know how to draw 60 degree, 120, bisect that. You guys know how to draw perpendicular at this point. So please draw that and then cut a length of 1. So let's say that is your 1. Now you join from 0 to this. There is your Pythagoras triangle, and this is having a length of root 3. Now all you have to do, very simple, just keep your compass point again at 0. Measure the length root 3 over here and just bring down your compass like this, and accurately you will get not 1.732, but this will be the accurate representation on the number line of square root of 3 using a triangle of length root 2, and this is of length 1. How did I get this one? Very simple. All you have to do is put the compass here and mark a length of 1. Clear? That's it. That's all you needed to do. So this one is clear to all of you. I have a couple of questions for you. Now, how do you decide is 9 by 420 a terminating or non-terminating decimal number? Can you guys do that for me? Is it a terminating or a non-terminating decimal number? So again, to do this, first let's write 9 by 420. 9 is nothing but 3 times 3. So you should always make sure you simplify your fraction. What is 420? 420 is 2 times 3 times 7 times 2 times 5, right? I'm breaking it into its factors. You can see 3 and 3 will get cancelled here. But you can see that the denominator is having 2, 2, 5, but there is a 7 here. So what do you guys think? Will it be terminating or non-terminating? Clearly, it is going to be non-terminating, but repeating, recurring, because there is a factor other than 2 and 5. So answer is non-terminating, but also and recurring. Crystal clear? Last one. Radius of a circle is 7. Is the circumference of the circle a rational or an irrational number? So what is the circumference of a circle? See, circumference is 2 pi r. Now, a lot of times we are tempted to do this. 2 pi is 22 by 7 times 7. So we say, hey, 7, 7 cancelled. Answer is 44, whatever be the units. Rational number, right? What do you guys think? Is this correct? Ankit Shah is correctly saying irrational, but Riti Patel is saying rational. See, so some of you are saying irrational. So the mistake here again is, see, when you're in this chapter, in mensuration or all of that, 22 by 7 is fine, approximation. What is the wrong thing here? I have used the approximate value. If we use the accurate value of pi, So if I say, hey, no, don't do this, do 2 pi r, where this is 2 into 3.14159 dot dot dot, right? Whatever, times 7, then it will always give you a irrational number. So you have to use the accurate value. So the correct answer is irrational. Okay, so this was a trick question. So in summary, I would again remind you, please remember this important chart that we did. And the easiest way to remember it is with all these examples. So you should write down this chart. I've made it very simple for you, very clear. And please understand these words: terminating, recurring, non-terminating, non-recurring. Then this whole real numbers is going to be really easy for you. Okay. So hope you enjoyed this maths class on real numbers, or what we call as number systems, and hope the concepts are crystal clear. And do check out the other courses on our website if you haven't taken the other courses. And also please do share it out with your friends. So stay connected with Manocha Academy and just enjoy your learning.